February 2026. The Sun is erupting with its most intense X-class and M-class flares in years. Deep within the Earth, a rare 6.2 magnitude earthquake struck nearly 510 kilometers beneath Fiji's tectonic plate. Major astronomical events are just days away, yet the science tells a more nuanced story than headlines suggest. What do these signals really mean, and what do they not mean? Let us examine the data behind this pivotal month. NOAA's X-ray flux plot offers a direct window into the Sun's intensity. The vertical axis shows X-ray energy measured in watts per square meter, and the horizontal axis tracks time in coordinated universal time. Solar flares are categorized by their peak flux. C-class flares start at 1 millionth of a watt per square meter. M-class flares start at 10 millionths, and X-class flares start at 100 millionths. Each step up corresponds to roughly 10 times more energy, making the differences measurable. Early February brought a pronounced spike. Active region 4366 produced multiple M-class and X-class flares. On February 1st, a series of sharp peaks rose above the amber M-class threshold, followed by an X-class event that crossed into deep red on the chart. The largest event, an X8.1, registered in the early hours, with additional M1.8 and M1.7 flares on February 8th. These measurements confirm that solar activity is elevated and quantifiable, with active region 4366 acting as the primary source behind the recent surge. Coronal holes stand out as dark patches on solar images, revealing regions where magnetic fields open into space and allow solar wind to escape more freely. During early February, several coronal holes rotated into view, with wind speeds measured near 450 kilometers per second, almost double the background solar wind. These high-speed streams buffet Earth's magnetosphere, sometimes stirring up geomagnetic activity detectable by ground sensors. Meanwhile, plasma filaments, long rope-like clouds of cooler gas suspended above the Sun's surface, can become unstable and erupt, launching material outward. Both features are tracked closely by scientists, since their behavior often sets the stage for changes in space weather. The KP index translates these solar influences into a simple scale from 0 to 9. A KP value of 5 indicates a G1 geomagnetic storm, enough to trigger auroras at higher latitudes and minor radio disturbances. NASA heliophysicists use these indices to connect what is visible on the Sun to measurable effects here on Earth. A magnitude 6.2 earthquake was recorded at approximately 510 kilometers beneath the Fiji region, far deeper than most seismic events. This was a deep event compared with typical shallow earthquakes. The United States Geological Survey pinpointed the epicenter using a global network of seismometers, analyzing the arrival times of seismic waves, especially the gap between direct phases and phases reflected from depth. This method allows scientists to determine not just the location, but the precise depth of the rupture within Earth's mantle. Events in the 300 to 600 kilometer range occur within subducting slabs, where mineral transformations can drive the release of energy. The duty seismologist reported no tsunami warning because earthquakes at this depth do not displace the seafloor. This event stands out as a clear example of deep focus seismicity, distinct from shallow earthquakes that pose greater surface hazards. Deep earthquakes like the one beneath Fiji originate under conditions far removed from those that drive destructive shallow quakes. At depths between 300 to 600 kilometers, immense pressure transforms minerals inside subducting tectonic slabs. One process, known as mineral phase change, can trigger sudden shifts, such as olivine converting to spinel, releasing energy without the brittle faulting seen near the surface. Another theory points to dehydration and brittlement, where trapped water is squeezed from minerals weakening the slab just enough for rupture. Caltech's deep focus specialists say these mechanisms are unique to high-pressure environments and do not act as warning signs for shallow megaquakes. Decades of statistical studies show no reliable pattern linking deep events to surface hazards. The science is clear. While deep earthquakes reveal much about the planet's interior, they offer no predictive power for the quakes that threaten lives at the surface. February's sky offers two rare sights for observers and astronomers. On February 17th, an annular solar eclipse will trace a path across the Pacific and Antarctica. During this alignment, the moon stands too far from Earth to cover the sun completely, so the sun's outer edge forms a ring of light, often called a ring of fire. The key is the moon's apparent diameter, which is smaller than the sun's from our viewpoint, creating this striking effect. Just days later, Saturn and Neptune appear to converge in the night sky, separated by about half a degree, roughly the width of a full moon. This conjunction is purely visual, a result of orbital geometry, not physical proximity. No evidence links these alignments to seismic activity on Earth. Their significance is observational, not causal. Scientific claims about planetary alignments or deep earthquakes predicting surface disasters can be tested with a simple three-question checklist. First, is there a direct link to observed data? For planetary alignments, no measurable increase in seismic activity has ever been tied to their timing. Second, is there a plausible physical mechanism, published and peer-reviewed? Planetary tides are thousands of times weaker than the moon, and they have no demonstrated effect on Earth's crust. Third, do statistical studies show a real pattern or just coincidence? Decades of peer-reviewed research find no significant correlation. When a claim fails any of these questions, it is best set aside. This approach helps separate what is possible from what is merely popular online and puts the focus back on data and scientific reasoning. Solar storms and deep tremors remind us our planet's systems are dynamic, not distant. Real-time data, not speculation, shapes our understanding. Curiosity and vigilance remain our best tools. Stay informed.